All right, we're going to wrap up our vector unit by talking about some application problems. So specifically, we're going to talk about one more type of way that we can look at vectors, and that is using what's called a projection. And so we have our formula for projection, which might look a little bit scary, where we have a projection of v onto u, and it's the dot product divided by the magnitude of v squared, all scaled to vector v. It's easier to think about this as a kind of geometric piece. So a projection, if you think about two vectors, so let me just draw another picture real quick to kind of highlight this a little bit bigger. So there's a vector, and we're going to call that vector v. And then I have a different vector that is attached to it there, so they're tail to tail. If I'm curious about the vector, the projection, there are kind of two things that are working here. So I have, for my red vector, it has a horizontal and a vertical component. And so if I was to break that into its components, it would have a component there, and it would have a component up. And those are going to make up the red vector. What I'm curious of for a projection is if you can imagine that if we were to take a light and shine it down. So if I had a light that was shining straight down, excuse me, the shadow that would be dropped from that. So if we were to think about the shadow that our red vector would put onto our green vector, it's going to have a shadow that comes down like that. Right? And then what happens is this whole piece down here, that horizontal component, is what's called our projection. So that idea of basically how much of a vector goes in the direction of another vector is what we call our projection. And so, again, another way to think about it is I have this green vector u, how much of it is going in the direction of v, and that thing is going to be called our projection. Same idea if we were to shade in all of the pieces that were straight down. If we were to draw that light, project it down, we can see that we get that red vector there as our projection. So the way that the formula is going to work, there's different ways that you can think about this piece. One way is by using your right triangle trigonometry. So we can see here that this is a right angle, which means that we can figure out algebraically with our trig what this looks like. So if I had a triangle, and this is the magnitude of u, and this is some angle that I know, right? I can figure out w1, and I can figure out w2, given that I have some underlying vector that maybe goes further out, just by using sine and cosine. And that's really what we're going to look at if we go forward. So there's two ways you can do it. One is with the dot product, so you have your projection with your dot product. The other way is to drop it into your trig and realize that, okay, this piece here is my projection, and so my projection of, let's see the way I did it, u onto v would be the magnitude of u cosine theta. That is a fancy way to write w1. That's a number, it's not a vector, and so then I'm going to scale that by vector v, and that becomes what my projection would look like. You can also notice that you potentially have a scenario where you have a vector that looks like this, and then the other vector that you're looking at is obtuse. Okay? And so your projection, if you imagine extending this back out like this, it's the same principle. You would bring that shadow down, so everything in here, that becomes your projection that way. So we're going to do a couple of practice problems, and we'll probably use both of these to look. We'll use the projection, the dot product divided by the magnitude, scale times v, and we'll also just try to think about it geometrically, and can we find those pieces without having to use that formula. So here's our first problem. We've been given two vectors in their component form, and we want to figure out the sum of two orthogonal vectors. One is which is the projection of u onto v. And so we have negative 1, 5. It gives us this point here. Looks like they have that labeled incorrectly, but graphed the right way. So negative 1, 5, that should be a positive 5 and the negative 1. And then we have 4, 6, which is over here. So we're basically trying to figure out these two components. Now if we see here that my shadow, right, if I'm looking for the projection of u onto v, and I drop down the shadow here, this component, W1, is the projection. So I can find that if I had the angle, right? So I can realize that I actually don't know what the angle between them is, so that makes it really hard to use my trig when I don't know an angle. So we're going to have to use the other formula that they showed us that involves the dot product. Alright, so that's kind of our setup. So when we look at this, we're going to find the projection by using the dot product. So we take the dot product of u and v, which we can do by just, remember, multiplying. So negative 1 times 4 plus 5 times 6 is negative 4 plus 30, which should be 26, divided by the magnitude of vector v. Okay, so we make sure that we get the order correct. When we don't do the projection of u onto v, we do the projection of v onto u. And so what we have here is we take this squared plus 6 squared, take the square root, and we get 52. So this becomes our scalar value, and then we multiply that times vector v, which is what we have here. All right, so it gets some modified vector at the end, and that would be, if we go back to our picture, what we're finding is this, W1. So we found that using the projection formula. All right, and now we need to figure out W2. Now if we remember, W2 was that other side of that triangle. So we had our vector going up. We just figured out W1, which is down here, and then we're looking for W2. All right, and so we can see that we've added these two vectors together. So I have vector u is right there. If I was to draw these as vectors, we go from W1 and then W2 going head to tail, what that means is vector u equals W1 plus W2. Well, if I'm looking for W2, what I can do is just subtract W1 from both sides. So u minus W1 equals W2. So that is geometrically what we're going to do algebraically as we go through this. Right, so we now have that those vectors line up that way. We can subtract them, and then since they're in component form, it's not very hard to do. Right, those are our vectors, and then we subtract them in component form, and that becomes W2. Right, so we have, at the end, we've figured out those two pieces. Right, so we have, again, this is W1 is calculated with the projection formula, and then we just use the fact that vectors are adding, in this case, head to tail. Right, so I have head to tail produces the resultant vector, and I can then subtract to get the one that I was missing. All right. So you need to kind of go through the same thing with this one. I'd really recommend drawing a graph to start so that you can get those pieces in the right spot. And then you're going to find the projection using the projection form with the dot product, and then you can use the geometry of how the vectors are added up to find the other component. All right, we're going to use a couple more word problems here. One is to figure out a final force. And so we have a 10,000 pound boulder that sits on a mountain at an incline of 60 degrees. In this case, we're going to ignore the force of friction. We're just going to look at the force of gravity. What force is required to keep the boulder from rolling down the mountain? So if we think about what's happening, and we have a picture on the next slide, is we have a boulder that's sitting up here, and its weight is directly down into the earth. We have an angle of 60 degrees, and basically what we want to do is we want to think about, we need to counteract. So if we are thinking of our vector, that's our weight, which is what, 10,000 pounds? Okay. Some of that is down the hill. So if this is my mountain, So if my mountain slope is like that, I have the weight of my rock going down the hill, and I want to figure out how much of that is going into the hill and how much is going down. Now, a really common mistake with this is we're trying to build a right triangle. We know that this angle is 60 degrees, and so what often happens is students will make this triangle. They'll go like this, and that looks good, and then we have a 60 degrees right here. Okay? That's going to be incorrect if we think about it. So if this is our setup, right, what we found is this is the thing down the hill is now our hypotenuse, okay, which means it's bigger than 10,000, which means what we're saying is it takes more than 10,000 pounds to keep that rock up the hill, which doesn't make any intuitive sense. Right? It can't be more force. We all know this just intuitive. If it's on a hill, I don't have to be able to lift the boulder, right? I just have to be able to stop a part of it. So we don't want to draw our diagram that way. Another way to do it is to think about, all right, that's going to be my biggest piece. This is what my setup's going to look like. I have some of that force that's going down the hill, and I have some of it that's going into the hill, and that's how those components are going to break up. So I have, that's the force down the hill. That's what I need to counteract. So basically I need a vector that's going to be going in the other direction of that force. So now what we need to do is figure out what to do with our 60. So our 60 degrees is the angle of our hill. And so what we need to do is that's going to be one of these angles in my triangle. All right. If I draw it a little bit better, bring it up a little bit, what we're going to see is that that 60 degrees actually could be drawn like this, where I have a 90 degrees here. What I have is two similar triangles. I have they share an angle, which is this angle, and they share 90 degrees. And so since they have two angles the same, the third angle has to be the same. And what we can notice up here is that that angle then has to be 30 degrees. And so if we have that setup, we can solve. We have a 30, 60, 90 in this case, and we know one of the sides, which is 10,000. And so we could solve and figure out that purple vector, which is the force down the hill. So that's one way to approach it. That's not the way the book does it, because another way to think about it is to think about a projection. Really what this is I'm worried about, I have the green vector, that's the weight. I want to project that value onto the hill, and then basically counter that. So we're going to look at their algebraic solution. This is the kind of geometric standpoint, and we'll look at the algebraic solution to how you would solve this. Alright, so basically they're going to find a unit vector that's in the direction of the mountain. So they want to know what is this going up as a unit vector, again a magnitude of 1, and then we're going to just scale that by the projection, the thing that's going down the hill. So to figure out the unit vector, we just take our magnitude of v, and then our sine and cosine values, and add them together. Alright, so we have our our unit vector, where I have my values of 1 and 1. I want that to be the magnitude, so cosine and sine, and that's going to give me my unit vector as a projection. Now my projection is my force dot plotted with my vector I just found over the magnitude of my vector times v. Now since I picked a unit vector, the magnitude is 1, so the magnitude squared is going to be 1, so divided by 1 just basically gives me the dot product. So I have this dot product times vector v, scale by vector v, which is going to give me that value. So if we look at their next piece, right, we're basically taking that value, alright, so we're taking our force, so this is straight down, negative 10,000 is the direction to go down, and that's my weight, dot product with my unit vector, and then scale that by vector v. So again, the dot product, I just multiply 0 times a half, negative 10,000 times root 3 over 2. These should look familiar. Remember, we actually just showed that it was a 30, 60, 90 triangle, and those are my 30, 60, 90 values for if I have on my unit circle where I have a radius of 1. Same thing here. And then I get my value of negative 5,000 root 3, or this value at magnitude times scale by vector v. So that's the force that's required to keep that up there. right? So again, that's 8,600 and change pounds of force to keep that from rolling down the mountain. This will always be less than 10,000, and if we were to decrease the angle, right, make it less than an angle, we'd expect this number to go down. If we were to increase this angle, we'd expect it to go up because more of that force has to be counteracted as that is rolling down the hill. Alright, so you are going to try to solve this one. You can look at it kind of two ways. It's the same idea. We have a car that's going to roll down the hill. We have an angle. Right, it's kind of drawn for us, the correct triangle here where we have our force going down. So you can try to figure out where the 15 is going to go, or you can use your dot product and projection to figure out the force to counteract that going down the hill. Again, beware, you know you're going to have an issue if you have more than 5,000 pounds that you have to counteract going down the hill. And at a degree of 15, you should have significantly less than 5,000 as your force that's going down the hill. Okay, our last topic here is defining work in terms of physics. And so one way that we define work, not just everyday kind of colloquial terms, but work is going to be defined as force times the distance that something travels. So the force that you put in that direction and then the distance that it goes. So if you are pushing on a wall and it's not moving, even though you're getting tired, you're not doing any work because there's no distance attached to it. So we need to keep that in mind. We'll be most efficient if all of our force is in the direction that we want it to go. That's not often the case. So often we have force at some angle, and then only a part of that force is actually pushing the object along the direction that we want it to go. So a lot of this will be determining how much force is going in the direction we want, and then just multiplying that by a distance. All right. So the way that we can look at our work is basically, again, I'm looking at a projection. I want to know how much of the force here is going in the direction that I want. So if the projection of the force along that vector scaled by times the magnitude of the vector that we actually moved it. So from A to B is a distance, so that magnitude goes there. And then we can solve that using our projection, all right, and get that the dot product of force, dot product A, or AB, our vector, is going to give us our work. So we can look at an example of that on the next page. But again, if you keep in mind that work is force times distance, and that force has to be in the direction that I'm actually interested in traveling. All right. So I have a person pushing a mower, and I want to know the work done by moving 12 meters. So what we have, right, is the 12 meters. That's going to be my distance. And then what I need to figure out is this 40 newtons. That's my force. Now I can't just take the 40 newtons and multiply it by 12 because the 40 newtons is in this direction, right? So we have the direction here going down. That's my force. And not all of that 40 newtons is actually moving it in the angle that I want to go, along the distance that I want to go. You can see that AB is down here, and that is going across. So while that distance is 12, we need to figure out how much goes in there. So this one is a little bit easier because it's given us our angles. So what we can see is if I was to actually just draw this out, there's my 40 newtons. That's a right angle. And then I've been given that this is 45 degrees. So this is a 45, 45, 90 triangle, which means I can solve, that's x and that's x, if I figure out that component, right? So if I look at my value, x is 40 cosine of 45, which is some number. That number is the force, that's the projection of how much a force is going in the direction I want. So I can take that number and multiply it by 12 to get my final value. So that's what we're going to do. We're going to look at it that way. Alright, so we know that we have a projection for our force, and then we have the magnitude of AB. This one is easy because it's just given us 12. The projection is a little bit trickier. So when we're figuring out the projection, it's just what we just had, right? It's that value 40 cosine 45. That's the component that goes in the direction. That's our distance. Work is force times distance, and I get a final value of 339. All right. You could also take this by using the dot product formula for work, where you would take the force dotted with the vector. All right. This one, again, to do that, we'd have to actually solve the components. So same idea. 40 cosine 45, sine cosine negative 45, and then my vector, my direction, is 12, 0. This will be easier if we have something that is going at an angle up and it's not straight horizontal or vertical. Be a little easier to use this formula. So when I take the dot product, again, my dot product, I'm going to take the first term times 12, the second term times 0, and we can see we're going to get the same thing that we got before, where we get 40 cosine 12. 40 cosine 45 times 12, and we get our final value of 339 joules of work. All right. This is one for you to figure out. You can use the projection, the dot product formula, or you can do it geometrically. Again, keeping in mind that work is force times distance. You have a force of 30 newtons, and then you have 8 meters as a distance. You have to figure out how much of this 30 newtons is actually going in the direction that you want it to go.